righty. Welcome, everybody, to the November 2024 meeting of the Central Florida Astronomical Society. Thank you, everyone, for taking time out of your day here to be with us. I am Frank Kane, your president for yet another year. So season 2, if you will, has begun here for our Zoom series of lectures. And just to give you a little bit of a preview of what we're going to be doing tonight. Oh, wait, before I get started, if you're watching this on YouTube after the fact and you're not a member of CFAS yet, well, you should join. You should fix that problem. So why would you join CFAS, the Central Florida Astronomical Society? Well, you get access to our private events and dark sky viewing locations, which we'd like to spend more time at, but the clouds have not been cooperating lately. Hopefully that will change soon as the weather starts to turn for the winter. We also have a loner telescope program led by our excellent Christopher, running the Loners program at loners@cfas.org. That's a very popular program where you can borrow a telescope and check it out for a few months and try before you buy, if you will. We also have an active online community at cfas.groups.io on the groups.io platform where we all chit-chat about astronomical stuff. And one of our best benefits, quarterly meetings at the Seminole State Planetarium, which is a very cool venue for astronomy geeks like us. And our next one is next month, along with our holiday party, which we'll talk about more shortly. Also, your membership, as of now, includes Astronomical League membership. We're going to talk about that a little bit more in a bit as well. And remember, we are a nonprofit 501c3 organization, 100% volunteer powered, so every dollar of your membership goes toward our outreach activities and supporting club operations, so you can feel good about that. And if you want to join, check it out at https://cfas.org to learn more and see our membership plans. Tonight's agenda, our main speaker book tonight is Geoff Chester of the U.S. Naval Observatory. He is just recently retired. In fact, he retired November 1st of this very month, so I'm hoping he's getting my messages because it's been a little bit of a confusion as his DOD email address is no longer working, and I've been contacting him on his personal one, but hopefully he'll be joining us shortly. However, there's much more to talk about tonight. I do have a lot of club news to go through, so I'm going to kick it off with that while we wait for Geoff. And John Pinto is going to have a book review for us tonight, Simply Stargazing, a potential stocking stuffer for you by Jonathan Popelle. And of course, we have our astrophotography showcase, which is awesome this month, I must say. And I am going to mute everybody except for me. If you do have something to say, though, feel free to use the little reaction icon down at the bottom of the screen and raise your hand, and I will hopefully see it and let you talk. Let me let in a couple more people here. So we'll get back to Geoff once we get him on board here, but let's jump ahead to club news. So Geneva Dark Sky Nights are back in action, and the weather, like I said, has been a little bit dodgy, but hopefully that'll be changing soon. Our next event is going to be November 22nd to 23rd. We also have the site booked for December 6th through 7th and December 27th through 28th. So as always, keep an eye on groups.io and your email notifications from that to get the final word on whether or not we're a go or a no-go based on the weather prior to those events. For those of you who are new to the club, Geneva is our dark sky observing location out in, well, you guessed it, Geneva, Florida, at the Seminole State Gun Training Range for their law enforcement program there. Again, just keep an eye on your email notification for more news on that and when it's happening. Also, next week on Wednesday, November 20th at 7 p.m., our own John Starr will be hosting a narrowband image processing workshop using one-shot color cameras. So that should be a very good session. John Starr is one of our most talented astrophotographers in the club, and any opportunity to learn from him is valuable. Hopefully, we won't be battling off another hurricane that night. If so, stay tuned for details on what might be happening. Let me let in a few more people here. And in other news, Christopher Hunt has launched a smartphone smash photo contest. So the idea there is that if you have any photos that you've taken by putting your cell phone up to the eyepiece of your telescope, you'd be amazed how good those can actually be. So if you got one you want to share and throw into the ring, contact Christopher at loners@cfas.org, and there may be valuable prizes that we're giving out for that at the holiday party next month. So put your name in the hat, show us what you've been doing with your smartphone held up to your telescope. Also, some good news. We're adding some C stars to our Lonerscope library. So we're going to be getting one of the S50s and also one of the brand new S30s that aren't available yet, but we're going to be in line to get one. Those C stars have been very popular with the club as a very easy way to sort of push a few buttons and get some instant gratification of deep sky targets. So we're very excited to start getting those in our Lonerscope library and letting them out to our members. All right, big news coming up. The CFAS holiday party is coming up soon. And thanks so much to Isabel Chaufeton, our events chair, for doing all the logistics for making this happen. It's going to be awesome. Registration is required for that event. We only have room for 70 people, and it is already sold out. So if you are signed up and you don't think you're going to be able to come, please do the right thing and let us know so we can free up space for somebody else. It's going to be a good night. It's Saturday, December 14th, 6 p.m. at the planetarium, and we're going to kick things off with some really cool stuff. But before that, we have a couple of bits of business to take care of while we're there. We do need to vote on the 2025 budget and approve that per our bylaws, so that should be a pretty quick piece of business there. Nothing too surprising that I'm anticipating for that one. The one thing that we do need to think about a little bit, though, is that we're going to be voting on whether we want to make Astronomical League membership an optional add-on for your CFAS membership or not. Doing so would free up quite a bit of cash for the club, in the long run at least. But, it does mean giving up your copy of the Reflector magazine if you do opt out. But the idea is to make it sort of a $10 add-on to your membership purchase if you do want that added benefit. Today, that's included in your membership. But in the end, it's up to you, the members, to decide if you want to make that move or not. We will honor whatever you guys say at the holiday party for sure. We're going to kick things off with the Star of Bethlehem Planetarium Show that's being presented by our friend Michael McConville, who will be presenting remotely through the Planetarium Dome. That should be a fun one. After that, we're going to move over to the classrooms where we're going to have all the food and everything. We'll have a presentation about the International Space Station by our own Amy Thompson, and we'll be announcing the winners of that smartphone smash photo contest I just talked about, and also a catered dinner. It looks really good from River City Catering, all for free, part of your membership benefits. And finally, we'll have Space Bingo with some exciting prizes as always. So that's going to be fun stuff. A little bit more interesting than the raffles we've done in the past, I hope. And also, we have a bunch of upcoming events as well. Something that's really cool is that we're going to be launching an art exhibition at the Orlando Museum of Art in April. And that's currently booked for one day on the 17th, but it might extend a couple of more days. So stay tuned for more details on that. And if you're an astrophotographer or artist or sketcher or whatever it is, and you're interested in exhibiting your pieces at this, please let me know at president@cfas.org, and we'll see what we can do to make that happen. We'll be going out on a little recon mission next month to kind of like check out the space and see how much room we have. But that's really awesome stuff. And again, thanks to Isabel for making that happen. Also, we're being very much involved with the ARIS program. That's the ISS Live Link Up with students at the Sally Ride School. CFAS has been very active in supporting that event. We've been providing them with guest speakers, and we're also going to be doing some observing events in association with that as well. So we're excited to be a part of that as well. And I have a little bit more news to get through here. First of all, congratulations to our new board members that were just elected in. So congrats to Sharifa Gassel, our new vice president, Debbie Vaughn, our new secretary, and Wes Clem, our new board member at large. Really stoked to have them all on the team here. And also a huge thank you to our outgoing members, Derek Demeter, Denise Woody, and Mark Pernal. They'll still be involved in the club in different capacities, which I'm happy to say. Everyone's a huge asset to the club. And of course, thank you to the people continuing on with the board of directors, John Frank, our treasurer, John Pinto, board member at large, Christopher Hunt with our loaner program, Sam Selig, our membership chair, Tricia Smedley on education, Amy Thompson with publicity, Douglas Woods running our amazing outreach program, and Isabel Chaufeton running our events. And just one more reminder, as we reach the end of the year, your donations to CFAS are tax deductible. We are a 501c3, so if you're giving out some charitable donations as part of your tax strategy, remember, we're here too. And if money isn't your thing, that's okay too. Tell your friends about CFAS. We've got about 200 people in the club now, and there's always room for some more. But if you're interested in donating, hit that donate button at cfas.org. Bunch of outreach events coming up, so thank you everyone who participated in the October events at Orlando Science Center, the Europa Clipper Star Party, the Spooky Star Party at the Planetarium, and also at Goldsboro Elementary and the Sally Ride School. Your names are all up there, so thank you, all of you. Coming up, we have a lot more outreach events lined up at the Heritage Middle School, another OSC event, the Cascades of Groveland event, and at Winter Springs Elementary and Enterprise Elementary. If you do want to get involved in outreach, contact outreach@cfas.org. And we have a whole subgroup for that set up for planning all the logistics around that. Very rewarding activity to get out there with telescopes and share that with kids. So do that if you can. On the astronomical calendar, in November 16th, kind of an interesting thing, the moon will be inside Pleiades. I'm not sure how much you'll be able to see the Pleiades because it's an almost full moon, but a really cool event there. Also, the Leonid meteors will be the next night, but again, with a bright mood, so might be tough to see. November 27th is kind of a neat one. If you're into occultations, this is a good one to start with. The moon will occult the star Spica, which is one of the brightest stars right now in the night sky. So definitely check that out if the clouds cooperate. And Jupiter is nearing opposition, December 7th in particular. So if you're into planetary imaging or planetary observing, that is the best night of the year to do it. And right now it's pretty good too. So watch that seeing forecast and get out there to check out Jupiter. The Gemini meteors will peak on December 13th, the day before our holiday event. And also another interesting event is Moon and Mars will be within 1 degree on December 18th. So that should fit within one field of view for a lot of the photographers in our club, a little imaging challenge. And of course, the winter solstice on December 21st, the happiest day of the year for astronomers. And we're going to get back to John Pinto after our main speaker, but let me roll things back. Well, actually, I'm just going to stop sharing and hand it over here. Stop share. So welcome, Geoff. I do have a little bio here. Are you all lined up and connected here?
Oh, I hope so.
Thank you so much for joining us.
Sure.
So, I do have a little bit of a intro here for you. So, Geoff Chester has recently retired, and very recently, I should say, November 1st, right? From
That's
the
correct.
USNO.
And I just got my official notice from OPM today that I am officially retired. So,
That sounds very official.
yeah,
Uh, but wow, what a run! You were the public affairs officer and historian after 27 years at the U.S. Naval Observatory. And by a curious quirk of history, you're the great grandson of the observatory's 15th superintendent, the Rear Admiral Colby Chester. Prior to coming to USNO, you spent 19 years working in various capacities for the Einstein Planetarium at the Smithsonian's National Air and Space Museum, and you're a past president of the National Capital Astronomers, an active member of the Northern Virginia Astronomy Club, the Association of Lunar and Planetary Observers, Dark Sky International, one of our favorites, and the Alliance of Historic Observatories. Welcome, Geoff. And as
thank
a,
you.
yes, and I brought along my treasured 1961 edition of the
Ah,
Explanatory
yes.
Supplement, by the way.
There is a newer edition out in case you're interested. So,
I think I have that one too, but there's
yeah.
some information in this one that just doesn't
Yeah,
appear anywhere
it's
else.
with the thing, it's funny, it's pretty arcane stuff, but it's amazing how some of it is still relevant today. And that's one of the things the observatory's been producing the Nautical Almanac for the United States, starting with the year 1855. And one of the parting gifts that they gave me was the 1953 edition of the American Ephemeris and Nautical Almanac. That was the year I was born, so I can
Wow.
look back and see all the stuff that was happening back when I was, maybe figure out why I got interested in this crazy subject to begin with. But anyway,
That's amazing. Yeah, I work on flight simulators, so it's my day job. And there's data from this very book that's still being used today for actual flight training. So,
yep,
a huge, huge valuable resource. Let me hand it over to you, though. You got some slides lined up here?
yep. All right, let me pull up my pre. Whoops, wrong button. It's always the wrong button.
Oh, yes.
There we are. Okay, so I want to bring up my little thingy here and start my show from the beginning and share my screen. There we go. Whoops. Ah, oh,
Not
wait a
seeing
minute.
it
There
yet.
we are. Okay.
All right.
There
Well,
we are.
well, great.
Okay.
Oh,
Very
quick note.
good.
Apparently, I misspoke earlier. The holiday party is December 14th. I have no idea what I actually said, but yes, December 14th. Sorry. All right. Yes, we see you.
All right. Okay. So my talk is basically Sky with Ocean Joined, scaling the stars at the U.S. Naval Observatory from 1830 to the present. Most people don't realize that the Naval Observatory has been around for a very long time. In fact, we are probably the oldest continuously operating observatory in the United States. The idea behind us started off actually was originally proposed by John Quincy Adams when he was president, and he was, needless to say, kind of not that popular. And so any proposals that he introduced to Congress were summarily shot down. But we'll get to that in a minute. Let me make sure that this will work here. Okay. There we go. Okay, so hopefully, there we are. So it's a little bit about me. On the left is a more or less freshly minted graduate of Worcester Polytechnic Institute with a degree in physics, attending Stellafane in 1976. That telescope is a 3-inch Merz Utschneider und Fraunhofer refractor that my brother-in-law found in a junk shop in New York City. I and members of my astronomy club in Massachusetts restored it and displayed it up at Stellafane. And we did such a nice job of it that my brother-in-law gave it to me. So that was kind of another telescope to add to my collection. But obviously, working at the Naval Observatory, I have access to somewhat bigger instruments. So I've managed to spend quite a bit of time with the 12-inch Clark Sagmuller refractor that is on the right side of the picture. The one thing about retirement is that I had to turn in my common access card, so I no longer can access the base, which means that I can't use the telescope anymore. So we'll have to figure out a way to get around that. But don't worry, there are folks there that are trying to work that problem as we speak. So I want to start with the beginnings of the Naval Observatory. As I mentioned, the idea for an observatory was originally proposed by President John Quincy Adams in his first address to Congress on December 6, 1825, when he proposed two things. One was a national university. The other was an astronomical observatory to be associated with that national observatory. And he lamented the fact that in the continent of Europe, there were dozens of these so-called lighthouses of the sky. And on the American continent, there were none. And he thought that was nothing less than a national disgrace. His pleas, though, fell on deaf ears. The funds were never appropriated for an observatory or the university. But along about 1830, late 1820s, a Navy lieutenant by the name of Louis Goldsborough, gentleman on the far left, was delivering a ship to the Asiatic Squadron, brand new 74-gun ship of the line. And obviously, they had to, in those days, there was no Suez Canal, there was no Panama Canal. So if you were leaving from the east coast of the United States, you basically sailed east across the Atlantic Ocean, made landfall to reprovision in Africa, sailed around Cape of Good Hope, and eventually across the Indian Ocean. And if your navigation was good, you wound up in Singapore or Hong Kong or whatever your destination was. Well, Goldsborough and his crew were some 45 days out of New York and expecting to make landfall in the west coast of Africa. And they woke up one morning and they found themselves bobbing around merrily in the middle of the Cape Verde Islands, approximately 150 nautical miles away from where they thought they were. Well, this was a pretty significant error in navigation. And in those days, the tried and true method of navigation was the chronometer method. If you've read the book Longitude by Davis Sobel, you understand the trials and tribulations that the English clockmaker John Harrison went through to ultimately claim the longitude prize of 25,000 pounds sterling offered by the Royal Navy to the first person who could come up with a reliable way of determining longitude. And the chronometer method simply meant that you carried with you on board your ship a clock that kept time at a known location. Your job then as a navigator is to determine time at your unknown location, and the difference in those times is longitude. Now, the only problem is that I'm sure that all of you probably own more than one clock, And I am just as sure that none of those clocks keep exactly the same time. So a chronometer is useless unless you know how it compares to a timescale of known precision. And in those days, all the chronometers that the US Navy had were basically provided by clockmakers in Great Britain. And we would essentially rely on the clockmaker's determination of the daily rate of the clock in order to compensate for it whenever we read it. And the problem is that buying a clock was not a very it was not a trivial matter. You had to sail to England and come up with a fair amount of money and buy as many clocks as you could, and then sail back to the United States. And the transit was not exactly smooth all the time, so you really didn't have any idea what was happening to your individual chronometers. And this was the case with Goldsboro. As it turns out, he checked the navigation instruments, the sextants. He checked the navigators' reduction tables. They were using the British Navy's nautical almanac. Everything was by the book. The one thing that he didn't have any precise knowledge of was the rate of the chronometer on his ship. The clock maker supplied a rating card which said the clock gained about 3 seconds a day. But in reality, after Goldsboro did some rough trials on it, he found that it was actually gaining 12 seconds a day. And that error accumulates every day that you are at sea. And it can very, very rapidly skew the result of where you think you are. So once Goldsboro resolved the fact that the clock was not properly rated, he was able to continue the voyage and ultimately successfully delivered the ship. When he came back to the States, he wrote a letter to the Secretary of the Navy basically saying that the Navy needed an institution that could essentially rate chronometers. Uh, to do that, though, you have to build an astronomical observatory because the best available time scale that we had to rate chronometers was the time scale determined by the mean rotation rate of the Earth itself. And the only way you can measure that is astronomically. So Goldsboro wrote his letter to the Secretary of the Navy, basically saying that the Navy needed an institution, a facility where it could not only store all the instruments that were not being deployed on ships at sea, but also to be able to rate the chronometers locally so that when they went out to sea, everyone was sure that they knew exactly how the clock was supposed to perform. Well, Lieutenant Goldsboro had a few friends in high places. His father was the chairman of the Board of Navy Commissioners, which was the board that told essentially the Secretary of the Navy what to do. And his father-in-law was the Solicitor General of the United States. Never hurts to have friends in high places in Washington. 3 weeks after he sent his letter, Goldsboro got his orders from the Secretary of the Navy to establish in Washington the United States Navy Depot of Charts and Instruments. Interestingly, the order was issued exactly 5 years to the day after Adams made his request before Congress. So it took a while, but the first astronomical observatory in the United States was summarily established. It was located in Washington, not too far from what is now the old Executive Office building. And Goldsboro then proceeded to start rating chronometers and sending them out when ships needed them to sail the open seas. And 3 years later, he was relieved by the guy in the middle, Lieutenant Charles Wilkes. Now, Lieutenant Wilkes was a very interesting guy. He had a very interesting naval career. I could go into detail about just what he did, but suffice it to say, during the course of his Navy career, he was court-martialed twice and still made admiral. So just goes to show you that you can get away with just about anything if you try hard enough. Wilkes didn't want to commute down to that part of town. He had a pretty nice house that was located not too far from the site, present day site of Union Station in Washington. So we can see here the site of the depot on 17th and G Streets Northwest. That was where Goldsboro established it. Wilkes decided that he was going to move it over here onto a site that was on North Capitol Street, a few blocks north of the United States Capitol. Well, it was a great location, but there was this big building down here that had a dome on it that blocked off 10 degrees of the southern horizon and interfered with transit circle observations. But, they were the people that supplied the money that we needed. And so the idea of having them move the building and tear it down was going to be a non starter. Wilkes also happened to have, he was a man of fairly independent means. So here's the Capitol as it appeared about in Wilkes's time. And this over here is probably Wilkes's house. So this is how close it was to the Capitol building. And it became known for a while as the Capitol Hill Observatory. Wilkes basically did transit observations because those were what were necessary to essentially determine the rotation rate of the Earth. So the budget for the observatory was interesting. Was never they never had any money to actually purchase instruments. So both Goldsboro and Wilkes had to basically scrounge around where they could to come up with the necessary instruments to allow them to do their work. But Wilkes was able to borrow from a nice transit instrument from the Coast Survey. And with that, he summarily began making observations. And this is actually a logbook of some of his transit observations of various stars that were made in the year 1836. In 1837, he was appointed to be the leader of a expedition to take several ships along with scientists to basically survey the Pacific Rim. And during the course of that voyage, which lasted some 4 years, he was the next officer in charge, Lieutenant James Gillis, took over at the observatory at Capitol Hill. 4 years later, in 1842, Wilkes returned with an incredible trove of scientific specimens, and observations and drawings and whatnot. And the last thing he wanted to have in his backyard was an observatory. He decided that the time had come for that to go. So he essentially booted Gillis out. Gillis was fortunate to be able to find temporary quarters over on Pennsylvania Avenue. But once again, we find another situation where we have John Quincy Adams involved. The U.S. exploration expedition, as I say, sailed around the Pacific Rim. They sailed all over the place. They were the first people to essentially understand that Antarctica was not just some random island in the far Southern Ocean, but it was indeed a continent. And if you look at maps of Antarctica, particularly this section down along in here, you will see that to this day, it is still called Wilkes Land. Well, as I say, Wilkes came back with this huge trove of stuff. And once again, John Quincy Adams played something of a role in our fate. Because at the time that Wilkes came back, a man named James Smithson from England bequeathed his very sizable fortune, roughly $500,000 in 1842, which was just almost it was an astronomical sum in those days, bequeathed that to the government of the United States. And he bequeathed it to establish an institution for the increase and diffusion of knowledge. Well, John Quincy Adams was now a representative from Massachusetts, And he spoke in Congress about the need to build a fully equipped astronomical observatory comparable to the ones in Europe. And once again, his ideas kind of fell on deaf ears. But in the long run, a lot of the specimens and the scientific work that was done during the Wilkes expedition eventually went to be the foundation of the Smithsonian Institution, where I worked for 19 years. So we didn't get the observatory out of any of Smithson's money, but Lieutenant Gillis decided that he was going to go for it anyway. So he wrote a letter to the Secretary of the Navy saying, figured probably it worked for Goldsboro, it might work for me. He said that he was overwhelmed with work. By this time, the Navy had gotten much bigger. The inventory of 24 chronometers that Goldsboro had to deal with was now well over 200, and Gillis was swamped. So he wrote to the SecNav and said, if you can find $10,000, $20,000 in the budget, we can build a permanent site. I can hire staff. I can get state-of-the-art instruments, so on and so forth. Well, he didn't hear back as quickly as Goldsboro did. It was more like 3 months that went by, and the SecNav said, it's a great idea, but. So we kind of knew that that was not going to happen, at least from the Navy's point of view. Well, Gillis was also a native Washingtonian, and he knew how the game was played. So he figured I didn't get satisfaction through my chain of command. I'm going to go around it. And so he began going up and schmoozing folks on Capitol Hill, pleading his case. And he ultimately found a senator from South Carolina who was very sympathetic to his cause, and that Gillis had made the first American recovery observation of Encke's comet that year impressed the senator, and he promised to do what he could to help Gillis get the place that he wanted established. So in the first Congress of 1842, he proposed a bill that would appropriate $20,000 for the construction of a permanent depot of charts and instruments. And further, that $10,000 be appropriated immediately so that the work could commence as soon as possible. So Gillis finally got his wish, and he designed the buildings that were going to go into this, that were going to go to the site. He purchased instruments from the finest instrument makers in Europe. He hired the staff that was necessary to run the instruments, and most importantly, he hired computers. In those days, computers were people with adding machines and logarithm tables, but they were absolutely vital for the reduction of the astronomical observations. So in 1842, he really thought that things were underway. He'd done all the legwork to establish the place, began construction on it, and was fully anticipating that he would be named as its first director. However, as we say in Washington, no good deed goes unpunished. And because of that, it turned out that in 1844, we got a new Secretary of the Navy. And he was a native Virginian. And he wanted a native Virginian naval officer to be the person in charge of the new Naval Observatory. So he appointed Matthew Fontaine Maury to be our first superintendent. And just to make sure that Gillis didn't have any say in the matter, they got his detailer to send him to South America. Well, while he was in South America, Gillis actually established an observatory, one of the first ones to be built in South America, in Santiago de Chile. And that observatory today is the National Observatory of Chile. So Gillis was, all he could do was build observatories. He was quite the avid scientist and astronomer. So the instruments that we got were, again, state-of-the-art instruments from Europe. These are some of the transit instruments that we had. We had a mural transit, which you can see on the back wall. We had a transit circle, and that were used to make daily observations of the transits of the sun, the moon, bright planets, stars, all to establish not only timescales, but to establish the fundamental positions of these bright objects during the course of a year. Uh, the crowning achievement, at least at that time, was the 9.6-inch Mertz and Mahler Great Telescope, which at the time was the largest telescope in the United States. Quickly, though, it was surpassed by the Harvard Observatory's 15-inch. But this telescope was used very, very extensively by a number of astronomers. And one of the ones who was probably the most prolific was this gentleman here, James Ferguson. He made the first asteroid discovery from the United States in 1854 when he found 31 Euphrosyne. He discovered 50 Virginia in 1857 and 60 Echo in 1860. And he was one of the first, in fact, I think he was the first American astronomer to be awarded the Lalande Prize, and published over 90 papers during his career, and really began to put the astronomical world of the United States into focus against all of the well-established European observatories. Now, Maury would have been superintendent for life, but in 1861 there was this disagreement between Virginia and the rest of the Union, and Maury decided that he was going to essentially throw his allegiance to his home state. So he resigned his commission in the Federal Navy, accepted a commission in the Confederate Navy. Ultimately, when he retired from the Confederate Navy, he retired with the rank of admiral. And it was at this point that Lieutenant Gillis got his chance to be superintendent. And one of the first people that he hired was a young astronomer by the name of Asaph Hall. Asaph Hall figures very prominently in the history of the observatory, as we'll see in a few minutes. But he was kind of the junior guy when he started there. And one night there was a request from the White House to an official party of visitors, including the president, Abraham Lincoln, his various cabinet secretaries, and other high mucky mucks in the government, went over to the observatory. And since Hall was kind of the new guy, he drew the short straw. So he was the one that got to show him stuff in the telescope. They looked at the moon and the bright star Arcturus in the telescope, and then everybody kind of packed up and left. But a very interesting thing happened a few hours later. Hall was busy making double star measurements with a micrometer. That was one of his favorite things to do. And there was a knock on the trap door that was at the top of the staircase that wrapped around the pier and gained access to the 9-inch dome. And the astronomers were used to the fact that the taverns all closed in Georgetown at about 2, 3 o'clock in the morning, and it was not unusual for them to be interrupted by various people staggering their way home who thought they might just get a peek through the telescope just for giggles. So the astronomers had a tendency to roll a fairly heavy desk over the trap door so that no one could barge in on them. Well, the knocking gets more persistent. And after about 10, 15 minutes, Hall decides, all right, I'm going to give this bozo a piece of my mind. So he rolls the desk off, opens up the trap door. Up comes a stovepipe hat, underneath of which was Abraham Lincoln, who had walked from the White House, which is at 16th and Pennsylvania Avenue, over to the Naval Observatory, which is at 23rd and D Streets. That's about a 10-block walk, by himself with no bodyguards at 2 o'clock in the morning, because he had this burning question in his mind. And that question was, why did the moon look backwards in the telescope? In a previous life, Lincoln had been a surveyor, so he was used to using surveyors' theodolites, but they have erecting prisms in them so that when you look through the theodolite, up is up, right is right, everything looks the way it does on a terrestrial view. But he was perplexed as to why the moon looked backwards. Well, Hall very patiently explained to him that the telescopes of the day wanted minimal amounts of glass between the target and the eye, and that was just a characteristic of astronomical telescopes. And apparently it satisfied Lincoln. He walked back to the White House. But over the course of the next several years, he made frequent unannounced visits or informal visits to the observatory. And his son, Robert Todd Lincoln, was a very frequent visitor even after Lincoln was assassinated. Robert Todd Lincoln stayed in Washington for many years, spent many nights at the observatory observing with Asaph Hall, and became a very avid amateur astronomer. And when he retired and moved up to his house in Manchester, Vermont, the first thing that he did when he went up there was build a small observatory with a 6-inch refracting telescope. So the Lincoln family and Asaph Hall were kind of inextricably mixed at that time. So, what did Washington look like at this particular time? Well, we had the Capitol, which was being built with its new iron dome going up over here. And the Naval Observatory was over here on this hilltop. When they came to when it came time to choose a location for the observatory, they presented a number of choices to the then president, who was John Tyler. John Tyler was the first president who was not elected president. He was William Henry Harrison's vice president. So in 1842, they gave him the choice of 4 sites to choose from. And Tyler never really got to like Washington that much. He spent a lot of time away from it, or if he was in town, he was cruising up and down the Potomac River. And he did notice that there was this hilltop that was just east of Georgetown that looked like a great place to put an observatory. So he said, let's put it over there. Apparently, nobody told him that that part of the city was known then, as it is still known today, as Foggy Bottom. Let that sink in for just a minute. You can see here, this is where the Washington Monument is, right here, being constructed. And here is the Naval Observatory. Well, today, if you come out, you'll see that there's a huge amount of the river that has been reclaimed and filled in to make West Potomac Park and East Potomac Park, the area where the Kennedy Center and the Watergate are now located. But you'll also notice that there's this canal which runs down here. There's also a creek that runs down from Capitol Hill through culverts and empties out down here. And you'll see this area right in here, which is where some of those creeks and canals empty out. That was essentially the septic system for the city in those days. And this was all river bottom swampland that surrounded it over here. So the observatory site was surrounded on 3 sides by the biggest open sewer in town. Now, I don't know how many of you have had the pleasure of spending summer in Washington, July and August. It's probably even worse than what you might experience down in Central Florida. It gets very hot, it gets very humid. I would hate to have been an astronomer who was observing on the 9-inch telescope on a nice July or August evening, because you open that dome slit and the south wind is blowing across that swamp, which has been percolating in the 90-degree, well, 100-degree heat all day. It must have been aromatic, to say the least. And if the fumes didn't get you, the malaria-carrying mosquitoes would come in and finish you off. One of our later superintendents, when he was surveying trying to convince the Secretary of the Navy that we needed to get out of there, did a survey of the number of nights when we could use our largest telescope to its full capacity. And for the year 1879, that total was 20, which pretty miserable. So anyway, after Lieutenant Gillis, we began getting some serious people working at the observatory. Rear Admiral Charles Henry Davis did 2 terms as superintendent. He was the founder and established the United States Nautical Almanac Office up in Boston. And in 1865, he became secretary or superintendent of the Naval Observatory, and he moved the Almanac office down with him. And he brought with him Simon Newcomb, who is arguably one of the great, considered to be one of the great American scientists of the 19th century, even though he was Canadian. But he was in charge of the Nautical Almanac office for about 30 years, in addition to being an astronomer at the Naval Observatory. So we began accumulating very, very talented people to work at the observatory. One of the things that was lacking at the observatory, though, was a really, really world-class telescope. So the superintendent, who was chosen to serve between the 2 terms of Admiral Davis, was the gentleman on the left, Rear Admiral Benjamin Franklin Sands. They don't let you do that beard thing in the Navy anymore, which is too bad. He would have been a great Santa Claus at the holiday party. But he assumed command, and the first thing that he noticed was that there were institutions, colleges, some high schools, well-heeled amateur astronomers who had bigger telescopes than the National Observatory did. And he thought this was nothing less than a national disgrace, especially because of the fact that the greatest living telescope maker in the United States at the time was an American in the form of Alvan Clark and his sons. And Sands wrote to the Secretary or to the Secretary of the Navy in 1867 and 1868 in his reports, saying that this was nothing short of a national disgrace. And he was backed up by Simon Newcomb, who said that there was a practical scientific need for this because his ephemeris tables for Jupiter and Saturn were not accurate. He was finding that the actual positions of these planets were not agreeing with his predicted positions. Now, Newcomb was known for having a pretty big ego, but even he had to admit that it was probably his calculations that were not right and not the fact that Jupiter and Saturn were not behaving the way he thought they should. He knew of the existence of the planets Uranus and Neptune, and he also knew that they had moons around them. And if he could measure the periods of the moons around each of those planets, he could use Kepler's laws to derive their masses. And so he had a practical scientific need for a large telescope, and Sands had a patriotic one. So in 1870, $50,000 was appropriated, and an order was placed with Alvan Clark and Sons to construct what became known as the Great Equatorial Telescope. It was delivered to Washington in the fall of 1873, and on November 12th of 1873, it saw its first light. Last year, we celebrated the 150th anniversary of its first light, and the telescope is still in use for mission-related observing to this day. Now, Asaph Hall, by now, was getting to be one of the more senior observers. Simon Newcomb basically monopolized the telescope from 1873 until about 1876, so that he could do all of his observations to figure out the masses of Uranus and Neptune. But once he was done with that, he was not a really enthusiastic observer. So he and his assistant, Edward Singleton Holden, who later went on to become the first director of the Lick Observatory at Mount Hamilton, they would frequently go out in the evening, and if they saw a puff of cloud in the sky, they would declare it a cloudy night and adjourn to Georgetown for beer and oysters. That was, the way things were back then. But Asaph Hall took over in 1876 and was essentially the most prolific observer with that telescope almost to the end of the century. He discovered one of the first things that he did was he found, excuse me, one of the first things that he did was he observed a white spot in the equatorial region of Saturn. And he timed the transits of that spot as it crossed the central meridian of Saturn and established for the first time a reliable rotation period for the planet, which today is only about 10 minutes off what Voyager basically determined. Over a series of hot August nights in 1877, he discovered the two moons of Mars, Phobos and Deimos. So on this page, this is the actual logbook up here that has his observations of Phobos. And on this page over here, it's the next evening, August 18th, or August 18th. And of course, we all know it's not real until the boss sees it. He's in the dome with all the top brass from the observatory. And there's a cryptic note here at the bottom that says Newcomb made all the measures on this page. Well, if Simon Newcomb saw them, they had to be real. And I was able to use our 12-inch telescope to photograph Mars a couple of years ago, and there's Phobos right there. It was kind of fun to be able to photograph that particular moon from near the place where it was discovered. So one of the other great expeditions of the 19th century were the Transit of Venus expeditions. These were organized to establish a value for the astronomical unit, the fundamental distance between the Earth and the Sun, which up to this point had not really been known that well. Well, one of our astronomers, or one of our orbital mechanicians who worked under Newcomb, was a man named William Harkness. And he figured that if we could make very accurate observations of the transit of Venus across the face of the sun from many different locations, we could then use geometry and parallax to determine the parallax of Venus and the distance for the astronomical unit. So the Naval Observatory was put in charge of overseeing 8 expeditions that went to the far corners of the world in 1874, mostly around the Pacific Rim. And in 1882, they were a little bit closer to home, but those 2 expeditions allowed Harkness to come up with a good prediction or a good value for the value of the astronomical unit. These were considered so important that Congress actually appropriated $100,000 to fund them over and above the budget for the Naval Observatory. And there are a number of fairly famous astronomers in here. This is Admiral Davis back for his second tour as superintendent. This is Asaph Hall. That's Simon Newcomb. This is George William Friedrich Peters. This is, oh no, that's Asaph Hall right there. This is Henry Draper. There's a list of people here who are well-known astronomers from the 19th century. So it was one of the bigger expeditions that we mounted to the far corners of the world. There's Harkness and a transit of Venus plate from the 1882 transit. This was actually taken from a station down in Florida. The interesting thing is that over the course of the 2 transits there were some 1,700 glass plate negatives that were exposed of the transit. Only 13 survive today, and this is one of them. Well, as I mentioned earlier, we had that year 1879 when we had 20 decent nights to use the Great Equatorial Telescope. And by that time, we had a new superintendent. His name was Admiral John Rogers. He was the fifth generation of his family to be involved in naval warfare in the United States. Long, long line. He finally was able to convince his superiors that the Naval Observatory needed to move out of the horrible conditions at Foggy Bottom. At any given time down there, half the staff were sick. There were a number of them who succumbed to malaria. It was really a bad place to work. So Rogers looked at a number of sites around Washington and finally settled on a 75-acre farm in the hills above Georgetown. It was still within the confines of the District of Columbia, but it was away from the river and the smog and the malaria-carrying mosquitoes and the sewage, and it was out in the middle of nowhere, surrounded by agricultural property. In other words, a dark sky site. So he was able to convince Congress to purchase that site for the sum of a little over $50,000. And over the course of the next few years, we kind of had a number of stops and starts. Unfortunately for us, Admiral Rogers died in 1882 as a result of malaria contracted while working at Foggy Bottom. And the next few superintendents that we had were ancient Civil War admirals on twilight tours, and they really didn't do much of anything. So it wasn't until this is 1881 when we purchased the property. It wasn't until 1890 that they started construction. And no sooner had they gotten the foundations dug and some of the first walls built when they found that the contractor was using inferior materials. And so they had to tear everything down and start over again. The building was finally completed in 1893. And in May of 1893, we moved lock, stock, and barrel up from Foggy Bottom to this site. Now, one of the things that is kind of fun is that back in those days, the government had, I guess, a fair amount of clout. So they were able to hire one of the most prominent architects in the United States to design the observatory. His name was Richard Morris Hunt. He was probably not that well known today, but if you have spent any time up in Newport, Rhode Island, and admired some of those quaint little summer cottages on the ocean walk, like the Breakers, or if you have visited the Biltmore Estate down in Asheville, or if you have seen the pedestal for the Statue of Liberty in New York Harbor, those were all designed by Richard Morris Hunt. This was his first federal commission. Uncle Sam liked the work so much, they had him do some of the buildings up at West Point, but I never talk about those because, after all, I'm Navy. But this became our home, and we have been at this home since 1893. Well, when the Great Equatorial was moved, we found there were a number of shortcomings in the original mounting. So we still have and use the original lens, but in 1893, we commissioned Warner and Swasey to build the new mounting for the telescope. And so on the left, you can see what the new mounting looked like in its early days. It has been considerably modified since then. Today, it actually operates completely under computerized control. The lens has been taken apart and cleaned to the best of my knowledge, no more than 5 times since it was first installed in 1873. And here are some people inspecting it in the 1960s, which was the last time it was cleaned before 2005. So we have a saying that a dirty lens performs a lot better than a badly cleaned one. And that's still true to this day. Today, the telescope, as I say, is used for mission-related observing, and its primary mission is to observe the astrometric properties of binary star systems. However, there are occasions when the speckle interferometer camera does go into the shop for repairs, and on those occasions, we hang an eyepiece off the back of the telescope. The last time we had this was last year in November when we celebrated the 150th anniversary of First Light. So this is a picture of one of the evenings that we had there. And it is quite a thrill to be able to look through this instrument and see things like the planets Saturn, Jupiter, Mars. I have had the good fortune to have seen the moons of Mars through the lens that discovered them on a number of occasions during my career. We also installed other new instruments. The 6-inch Warner and Swayze Transit Circle was designed by William Harkness, and this was probably our most heavily used instrument. Went into service in 1899. It was used continuously up through the early 1990s. It made its last official observation on the day after the centennial of its first, so we can honestly say it was in use for over 100 years. Today, it stands as a proud reminder of the days of fundamental astrometry, the old-fashioned way, in the lobby of the main building. And we still have one employee who works there who actually observed with this instrument as part of his regular duties back in the late 80s and early 90s. He'll be retiring next year. Now, my favorite instrument is the 12-inch. This was a lens was made by Al Van Clark. The mounting was made by George Segmuller, who was a local owner of a machine shop in Washington and built a number of scientific instruments and about 10 or 12 telescopes of 10-inch aperture or larger that are scattered around the world. The largest one is in Denver, Colorado at the Chamberlain Observatory. So if you're ever out in Denver and visiting with the Denver Astronomical Society, by all means, take a day and go check out the 20-inch at the Chamberlain Observatory. The other telescope that we purchased was a 15-inch Warner and Swayze astrograph. This was something of a dud. The telescope lens was never properly, they just could never get it to work. It went back to Warner and Swayze at least half a dozen times. And finally, Warner and Swayze, World War II came along, and Warner and Swayze said, we don't have time to screw around with this anymore. So they basically abandoned the project. The lens was ultimately refigured, but we still had to stop it down to 8 inches in order to use it. But it was used for doing astrometric imaging of asteroids. But the main thing about the observatory is that as we developed our kind of our niche in how we fit into things, the main function of keeping precise time remained at the head of our mission statement. And so we employed a number of clocks over the course of the years to essentially keep time, and those clocks were regulated by observations that were made with the transit circles. We had 2 transit circles, the east and the west transit. The 6-inch is the one that is to the west. It's in this building over here. And of course, this being a Navy base, every building has a number on it. The main building is building 1. The 26-inch telescope building over here is building 2. This clock house over here, which is where these clocks were kept in the basement, that was building 3. But this is where things start to get a little kind of falling off. We put the 6-inch transit circle in building 7 and the newer 7-inch transit circle in building 6. And from there, the order just kind of gets random. But the idea was that you would take a mean of observations made with the two different transit circles to allow you to compute a time scale that you could then use to set the time on these very precise Riefler mechanical pendulum clocks. These clocks were very precise because the mechanisms were made out of Invar, which is an alloy that has virtually no coefficient of expansion, and they are kept in vacuum chambers. So there is no interference from temperature changes or air. In fact, these clocks were read by standing in a room upstairs, and you can just barely see there's kind of this funky thing that's hanging here. That's the end of a periscope that was used to look down through the floor at the clocks so that nobody actually had to go into the clock vault and potentially disturb them. These clocks were precise to on the order of better than 1/100th of a second per day. So very, very precise. So one of the main jobs that we had was rating chronometers. In Goldsborough's day, these were done individually by comparing the time on a chronometer with time determined by a transit circle. When you have only a dozen or so clocks to keep track of at a time, it's a fairly simple thing to rotate them from night to night to check on their running rates. But as the observatory grew and the Navy grew, we wound up with hundreds of clocks whose time we had to compare and to calibrate. And so this is one of the chronometer rating rooms here. There's a bunch of chronometers on the wall. There's another bunch of chronometers down here in this case, and more chronometers on the opposite wall. We also began transmitting time where people could actually do something useful with it and use it to set clocks anywhere around the country. So starting in the 1870s, we were hooked up to the Western Union network and began sending time every day at noon in the Eastern time zone once we went to standard time. And this was our standard transmitting clock system. This was circa 1901. And every day at 5 minutes before noon in the Eastern time zone, all the message traffic on the Western Union network would stop, and all the operators west of us would switch over to a dedicated telegraph circuit and await a synchronizing pulse from this clock system. This in turn would set the hands of a display clock in the Western Union office to the top of the hour in whatever time zone they happened to be in. And that way people had a reliable source of time no matter where they were in the country. Now, the problem with doing this kind of way or doing it this way is that setting time by transit circles has one small problem. And that is that the detector is one of these things here, an eye, and it is hooked up to a rather slow neural network to a brain. And the reaction time between when the eye sees a stimulus and the brain sends a signal to a finger to push a button to mark the time is different from each individual observer. So we needed to come up with a way to kind of get around that problem. And so we came up with a device called a photographic zenith tube. Now, the photographic zenith tube is essentially a refracting telescope that stares straight up into the sky. So the lens is located up here, and since it stares straight up into the sky, light comes down, goes through the lens, about half the focal length of the lens down in a well down at the bottom of this pit here. There is a pan of mercury, which reflects the light back up to a small photographic plate that's suspended just below the lens. So we set the clock to trigger the photographic exposure at a time when a star is supposed to cross the meridian. And if the clock is keeping accurate time when we develop and process the plate and examine it under a microscope, we can see that it is indeed on an etched line, which marks the position of the meridian on the photographic plate. But if it is not on that line, then we know that there is an error. And since we know what the rate is that the star is moving, we can determine what the clock error is. So this is a much more accurate way to determine time. It takes out the factor of a human's reaction time, and it allows us to send time to this clock over here, which was the last of the pendulum clocks that we used at the observatory. We employed those up through World War II, which is interesting when you think about it. It's a technology that's 300 years old, and we were still using it through World War II. The idea behind this one was that you had two clocks. This was the master clock here. This had a free pendulum in it that could swing and precess as the Earth rotated. There was no clock mechanism up here to dissipate energy from that pendulum, so it was essentially frictionless. And it was hooked up to an electrical network that would synchronize with a pendulum in a slave clock every 30 seconds. And you could then display precise time up here. This clock was accurate to about 1/10,000th of a second per day, which is pretty remarkable when you think it's a mechanical clock. But as technology improved, we had to adopt newer ways of keeping time. In the 1930s, we began experimenting with the first quartz crystal oscillator clocks. These were brought online in production capacity in the 1950s. So this is a typical quartz crystal clock that we had at that time. It stands in a rack that's 6 feet tall and it weighs about half a ton. Thank goodness for miniaturization, because today most of us are wearing them on our wrists. I would hate to have to lug that beast around. But in the 1960s, we began adopting this new technology of using what are so-called atomic clocks. Now, atomic clocks aren't what you think they are. It has nothing to do with radioactivity. All clocks basically are fundamentally two things: an oscillator and a counter. So if you can come up with something that gives you a periodic variation at a very rapid rate, you can make yourself a very precise clock. And what the atomic clocks measure is a specific microwave frequency that's given off when an electron in a cesium atom falls from a higher state to its ground state. And that frequency is very, very short because atoms are very, very small. And it is also incredibly precise. So now we need a new way of defining the second, because up to this point, the astronomical second was still king. So we had an astronomer named William Markowitz who decided that he was going to find a relationship between a particular astronomical time scale called ephemeris time, which was derived from the mean orbital period of the Earth around the sun, with the frequency of a cesium atom. And he essentially invented a special camera to photograph the moon against background stars and make very precise measurements of the moon's position from 8 separate locations around the world, all synchronized to a particular time. And after about 10 years worth of work, working in collaboration with scientists at the National Physical Laboratory in Great Britain, he was able to come up with a value for the duration of a second as defined by the cesium atom. And since 1967, the second has been defined as the interval of 9,192,631,770 hyperfine transitions of a neutral cesium-133 atom in the absence of external forces. I didn't tell you there was going to be a quiz after this, did I? All right. Um, so that is kind of the current generation of operational atomic clocks. We have refined that technology somewhat by creating what is called the rubidium fountain clock. This actually takes advantage of 5 Nobel Prizes in physics. Uh, One of those was awarded to this gentleman over here, Bill Phillips, for coming up with a way to use lasers to trap and cool atoms to incredibly low temperatures. Uh, we took this and designed and built our first and so far the only operational fountain geometry atomic clocks in the world. And as it turns out, this gentleman here, Steve Peel, who's the head of our clock development office, was one of Bill Phillips's grad students. So we're very fortunate that we can get people like him to come and work for us. The Navy rubidium fountain clocks are so precise that if we measure the difference between the ticking rates of any two of them on a day-to-day basis, those differences are measured at the femtosecond level. That's 1/1000th of a trillionth of a second. So you can imagine what it's like being late for work at the observatory. You got no excuses. Well, Steve and his cohorts aren't happy because they want to get even more precise time. So they are now working on optical frequency standards. And one of the reasons that I decided this would be a good time to retire is that sometime in the next 10 years, when these optical frequency standards become operational, the second will have to be redefined in terms of a frequency that is much, much higher than the current microwave frequency that we're defining it with. Uh, the head of our precise time department has told me that I will have to memorize an 18-digit number, which I said I'm not in any way, shape, or form ever going to be able to do. So my successor will get the dubious distinction of having to do that. So what is it about time? Well, time, I don't know. Time, from a philosophical point of view, nobody knows what time is. Einstein said it best. I think he said, "Time exists so that everything in nature doesn't happen all at once." These are all the various types of time scales that are applicable in the world today. But the one that is really important is this one here, Coordinated Universal Time, which uses international atomic time, which is defined up here as that atomic transition in the cesium atom, uh, with periodic insertion or deletion of leap seconds. This keeps the Earth more or less in time with atomic time, and it keeps the geodesists and the navigators happy. The astronomers, not so much. But there aren't that many of us, so who cares? So these are some key dates in the history of timekeeping in the United States. The this is the one here, the Uniform Time Act. This is what actually has our current policy, including that awful daylight time thing, which has been futzed around with, but hopefully they'll get rid of it once and for all. I'm frankly tired of setting up twice a year, having to set my clocks and answering all the dumb questions about it. So the Naval Observatory's footprint today is we have our site here in Washington. We have a dark sky site that was established in 1955 out in Flagstaff, Arizona. Flagstaff is a great place to do astronomy from. If you've never been there, I highly recommend a visit. You can stand on a moonless night in front of the great 24-inch telescope at Lowell Observatory, smack in the middle of downtown Flagstaff, and see the Milky Way very easily. We also have an alternate master clock facility that's located at Schriever Space Force Base in Colorado Springs. That way, if somebody trips over the big power cord here and knocks the clocks offline, we still have the capability of providing time to things like GPS. and the master GPS control center is located here at Schriever. We also have a dish antenna for radio astronomy that's located in Koki Park out on the island of Kauai. In my 27 years there, they never decided it was something that they should send the public affairs officer out to Koki Park to do some photography. I've been to Flagstaff plenty of times, but they never sent me on that trip to Hawaii. But anyway, I'll just have to live with that. So the headquarters today are this beautiful building. As you can see, we've got more trees that have grown up around it. And this is our Flagstaff station out in Arizona. These are some of the telescopes that we have out at Flagstaff. The largest astrometric reflecting telescope in the world. For those of you telescope nuts, this is a very interesting telescope. It is a Newtonian Cassegrain. It's basically a Cassegrain with a flat secondary mirror. This gives us a very long focal length for doing photometric or photographic and CCD parallaxes. This telescope is the 40-inch Ritchie Chrétien telescope, the last telescope actually built by George Willis Ritchie. It was in Washington for some 20 years, didn't do much there, but as soon as we moved it out to Flagstaff, it was used to discover, among other things, the polarization of starlight. And it is still in regular use today. The 61-inch telescope is responsible for taking images of Pluto. You'll notice it's got a little hump over here, like young Frankenstein. Whenever Igor comes up on the screen, he goes, "What hump?" And Jim Christie was reducing these photographic plates back in Washington when he noticed a periodicity between the hump being here and the hump being here of a little over 3 days. And it led him to the conclusion that this must be an unresolved satellite orbiting Pluto. So Bob Harrington from our Nautical Almanac office did the calculations and predicted the first orbit of Charon, and also predicted that it would start undergoing mutual eclipse and occultation events shortly after its discovery. And lo and behold, they happened. And we now know that Pluto has a very large moon, which unfortunately for Pluto, demoted it to the dwarf planet category. So you can blame us for killing Pluto. We still use a transit circle instrument. This is a robotic telescope that's out at Flagstaff. This is used for doing very high-speed real-time astrometry of near-Earth asteroids and other objects that have the potential to whack into us. So this telescope is in use every clear night out in Flagstaff. And it also helps to establish what's called the celestial reference frame. In the real transit circle era, first half of the 20th century, transit circles were used to fix the positions of bright stars. And those stars were then used to essentially, like surveyors' benchmarks, to determine the positions of fainter stars on astrograph plates. And from that, you could derive a star catalog. Well, the problem is that nearby stars or the bright stars are relatively nearby stars, and all the stars are moving, and the nearby stars are moving faster than the farther ones are. So every 50 years, you have to repeat your fundamental catalog to take into account proper motion and precession. Well, today we use a technique, radio technology called very long baseline interferometry, where we use radio telescopes around the world to make very precise observations of the positions of quasars. We track about 4,500 quasars and about 1 million active galactic nuclei to establish a virtually immovable fundamental reference frame. Quasars are and most AGNs are so far away that they show no component of motion on the sky except radially away from us, and therefore they make very good reference points. They also happen to be bright not only in the radio, but we see them in almost all parts of the electromagnetic spectrum. So they are great for fundamental reference. We still do put together astrometric catalogs, although the Gaia spacecraft is kind of putting us to shame on that right now. But we have a dedicated astrograph that we can use at Flagstaff and then send down to South America. And we can do what Gaia can't do, and that is make observations over a long period of time. So we can use this very large hybrid CMOS chip here, 440 megapixels. That's compared to a digital camera. We can use that at the business end of this telescope, and we can do these astrometric catalog observations over a longer period of time so we can derive proper motions of stars over a much longer period than Gaia can. And we can do this for something on the order of, I can't remember now, something on the order of a billion or so stars. So we still have use for that. This gives you an idea of the depth that this catalog can go to. Our TICO 2 catalog from 2000, which was based on the Hipparcos. This is Messier 11 is plotted with that catalog. This is Messier 11 plotted with the UCACS, which was the forerunner to the USNO robotic astrometry catalog in 2013. And the density of stars with the new technology on that astrograph. So one other department that we have that's a very important one that most people don't think about is Earth orientation. Most of us think of the Earth as a nice, fundamental, stable thing to do astronomy from. You know, you jump up and down on it and nothing seems to move unless you have your telescope set up on your roof or something like that. But the Earth is really, A, it's a terrible timekeeper, and B, it really doesn't rotate uniformly. Over time, we have a component of what's called polar motion. The Earth's rotational poles actually wander over a spiral pattern in and out with a period on the order of about 435 days. This motion means that the pole displaces from one side to another over a distance about the size of a baseball diamond. That's important when you are using things like GPS to find a ground position solution. If you don't take polar motion and Earth orientation parameters into account, you will get the wrong answer and the missile will land on the wrong target. And that's something that we definitely don't want to have happen. The other component is variation in the Earth's rotation period. This is the Earth's rotation measured over a period of several years, and it shows you the day-to-day variations, month-to-month variations. This is all tidal influence of the moon and whatnot, but you'll see there is a general deceleration in the Earth's rotational period. So this is why we have those pesky leap seconds. And eventually the time will come when we may see the Earth and the Moon in what's called a supersynchronous rotation, where a day will be the length of a lunar month, as is the case with the moon Charon, the moon of Pluto. Fortunately, that is a long way off. I think the odds are that the sun will swell up and expand and gobble up the inner solar system well before that happens. So that gives you hopefully an idea of a little bit of the history of the observatory as well as what it is that we do. And we will continue to do that, whether I'm there or not. But it's been an amazing place to work and an amazing place to share with people such as your group. So without further ado, if you want to look for us on the web, this is where you will find the observatory and you will find me. And with that, if anyone has any questions, I will be glad to take them.
Thank you so much, Geoff. I had no idea there was such a rich history to the USNO and all the stuff you were doing. So that's very cool. We do have a couple of questions queued up here in the chat. And if anybody
All
has
right.
a new one, hit that react button at the bottom and hit the raise hand icon, and I will get to you and you can ask your question live as well. One for me, though, are any of these facilities open to the public at all in Flagstaff or Washington?
Unfortunately, no. We conducted public tours up until 2017. And actually, we had to stop for several months after 9/11. The place was pretty well locked down. I was able to come up with a system that worked at the time so that we were able to reestablish public tours in 2003. But in 2017, the security of the observatory, especially the fact that we had these new atomic clocks there that are very highly proprietary, as well as the fact that basically we're the timekeeper for the Department of Defense, it was decided that we were a strategic asset and could only be accessed by military personnel or government employees. So I have lost my CAT card. I can't go on the base anymore.
Wow. Well, if anyone's looking for a reason to join the Navy, there's one for you right there. Thanks. We have a question from Luke. He wants to know more about what a transit measurement is and how it's related to the Earth's rotation.
Okay, a transit observation is simply a measurement of the instant that a celestial object, the upper or lower limb of the sun, or the moon, or the center of the disk of a bright planet, or a star, crosses or transits your local meridian line. That's the line from north to south through the point directly overhead. We can predict with some precision when such an event is going to occur. So it follows that if we can observe that event physically, we have something that can give us a check on our computation of current time. And this was the best available method that we had for measuring and creating timescales up until these more sophisticated clocks came along, which essentially outperformed our ability to calibrate them. So the atomic clocks today are now basically almost, they're not self-calibrating, but we have an old expression that a person with one clock knows what time it is. A person with two is never sure. So we take a numerically weighted average of the best performing of about 100 atomic frequency standards that we have at the observatory, and there's about 30 or 40 of them out at the alternate master clock facility. They are continually monitored, and we take a numerically weighted mean of the best performing of those clocks. And from that, we create our real-time realization of International Atomic Time and UTC.
Thank you. And you talked a little bit about the leap second being necessary due to changes in the Earth's rotation.
Right.
John Pinto wants to know if you can talk a little bit about the change to the leap second.
So the leap second, when it was established, it was in 1972. And in 1972, the atomic frequency standard to define the second was established in 1967, and everybody was like, "Okay, fine." But in 1972, it became apparent that there were significant differences between Earth rotation time, something that we call a UT1, and atomic time. And the physicists wanted to have a single uniform time scale. So they came up with a solution, which was to essentially have two concurrent time scales: International Atomic Time and Coordinated Universal Time. And Coordinated Universal Time is essentially Earth rotation time that is adjusted periodically by the insertion or potentially deletion of an integral leap second. Well, in 1972, this seemed like a very viable solution. It kept the astronomers happy, it kept the physicists happy, everybody was playing nice in the sandbox together. But then they started thinking about hooking computers together and hooking computers together over large networks and hooking computers together over large networks that span the entire planet. And now they started running into problems because if you don't have all of the computers in your enterprise essentially keeping exactly the same time, well, bad things are going to happen. Um, and the insertion of a leap second became an excruciating activity for system managers because if they did not add the leap second at exactly the right time across their entire enterprise, they would lose their connection to the outside world. Uh, Systems would fail, money would be lost, et cetera, et cetera. Every year when it has happened, at least in the time that I've been there, about 10% of the networks around the world fail because the system administrators didn't quite know how to deal with the leap second. The big poster child for that was in 2012. Qantas Airlines did not do the leap second properly, and they lost a day of operation to get all their computers back on track again. I don't know what the financial impact was, but I'm sure that the system administrator was kind of run out of town on a rail for that one.
Rightfully so. Awesome. And if anyone else has any questions, feel free to take yourself off mute and just holler. But if not, I'm going to thank you for letting us drag you out of retirement tonight. And
That's quite fine. Glad we were able to make it work out.
yeah, thanks so much. And so what's next for you? Like, what's coming up for you in retirement?
Well, there's actually talk that they might hire me back as a contractor,
Cool.
which would be good because then I'll get my access privileges back. But I will probably wind up working with the archivist and the librarian to identify old photographs, various and sundry instruments that we have in our instrument collection. Um, and That would be one thing. Uh, I've also got a few projects going on the side. There's a school that's out in Middleburg, Virginia, that has a very nice observatory that was built in the 1950s, and they want to restore it. So I'm consulting with them on that, and hope to get it up and running in the next year or so. And the main thing is that I have more time now to do my own astronomy.
Yay.
You know, it's kind of
Yeah.
funny. I worked at the Naval Observatory for 22 years or 27 years, but that a lot of that time was I had to work evenings up there for various functions and tours for high mucky mucks and that sort of thing. I've basically given tours to five of the eight vice presidents that have lived up there since I started in 97. Um, you know, and that kind of eats into the time that I have to use my own telescopes in the various places that I go to with my astronomy club. I have probably done more of my own astronomy in the course of the last 10 days than I have in the previous 10 years. So, there's that part of it too.
Excellent. That's something to treasure. Thank you so much for your time tonight, Mr. Chester. That's been
You're
a pleasure.
welcome.
Yes, and you're certainly welcome to hang out with us here for the rest of the night or get back to your evening. It's up to you. But yeah, thanks so much.
Okay, well, take care. I think I will bid you adieu and go and have some dinner.
All right. Sounds like a plan. Thanks so
All
much.
right.
Great.
Yep. Take care.
Thank you. And by the way, tonight's speaker was recommended by John Pinto, who is up next. So, John, you've
Oh,
got a book review for us, don't you?
Yes, I do. And I would just want to
oh,
thank Jeff. so much for indulging me. And I do want to say Geoff is a proud owner of a Sea Star, and he has done some really excellent photography with it. So thank you again, Geoff.
If I can just say, it's tons of fun. I can do stuff from my backyard, and I literally am located in a Bortle 9 sky. And I can do stuff with the Sea Star that I can't do with my other telescopes unless I decide to schlep them out to West Virginia or something. So it's a pretty remarkable little gizmo for the price. And I don't know if you saw my most recent posting of the Perseus Galaxy cluster.
Yep.
Just the fact that I could image them, from here, just blows my mind. So we'll see what else I can come up with.
Wonderful. Thank you again, Geoff.
All right.
All right.
John, I think I need to give you co-host privileges. Hang on.
All righty.
There you go.
Okay. Get into presentation mode here. Come on. You can do it. There we go. All right. So anybody who really knows me knows that I am a book hound. And one of the things I always try to keep an eye out for are books that people ask me, hey, I want to get into astronomy. I want to, well, how do I start? And I have a fairly large collection of those kind of books. And one of the recent ones that I've come across, I've really come to love, mainly because it is so easy to use and really get people started. So the fellow who wrote this book, Jonathan Popelle, had been teaching astronomy for many years and had produced a number of materials to help people get interested in astronomy. And to me, this is kind of the perfect intro book. It's called Simply Stargazing. And at the end of the presentation, I'll show you some of the other materials that he's created. So if you are interested in stocking stuffers, or everything that I'm going to show you here and at the end make perfect gifts, and they're all very, very inexpensive. So this is the cover. It's a very small, little handy book. It's probably about 30 pages long. It's a spiral cover. So, easy to pack away, bring out with you to the dark sky and start learning about the sky. So it starts off real simple. It's like, well, what do you do? This book is going to have 6 star maps, so it's not going to overwhelm you. It has charts for each of the season's most prominent constellations, so you can learn how to navigate around the sky. I'm not going to show you this piece of it, but it also includes something. I actually learned something I had never heard of before. He shows you how you can tell where the moon is going to be in the sky, like what constellation it's going to be in, just by knowing, a typical date that's published in the newspaper. Say, it'll say the full moon's going to be on this date, or the first quarter is going to be on this date, or the new moon's going to be on that date. Just using that piece of information, that date, and the chart that he has in this little guide will tell you what constellation the moon will be in on that night. So I had never seen that before, but you learn something new every day. It has a map of the moon, and I'll show you what that looks like. And he gives you some tips on identifying your planets, deep sky objects, best time of the year to watch for meteor showers. So again, all the basic things you need to just start learning when you're first coming into astronomy. Obviously, the typical things you always tell everybody, pack warm, bring this guide, bring a red light, bring binoculars, and to preserve your night vision. So the first thing that you see when you open this is what chart should you be looking at, depending on what month and part of the month you're looking in and what time you're going to be looking. And he very conveniently gives you daylight savings time times when it's in force. So you don't have to do any, plus 1 hour, minus 1 hour, whatever. So very simple to use. You'll notice at the top here that I have stuck a little sticky note in my book, and you're going to see a few of these here, because obviously all of these times are based on central meridians for time zones. Now, our central meridian is way out in the Atlantic Ocean from here in Orlando. So for us, we have to actually add 30 minutes to these times for our local time. So, if this thing says late April at 9 p.m. daylight savings time, you go to this chart and that's what you'll see. In reality, for us, it would be like 9:30 in the evening. So I have little notes in here about that. So this is the fall chart. So this would be perfect for using at this time of year. And I actually went outside the other night to just check this, and it actually is pretty accurate to where things are going to be in the sky when you were to go out. And again, my favorite direction to look is east, where the sun rises. And I find that helps me to understand pretty much where everything else is once I can identify where things are in the east. And the way these work is very simple. You need to know your directions. Okay, so you're gonna need a compass, or most smartphones have a built-in compass. Take it out, you figure out what direction you're looking, and then you just turn the book so that direction you're looking is at the bottom. So in this case, east is at the bottom. Again, my favorite direction. And I just look up, and that's what I see in the sky. You'll see I also have some little sticky notes at the bottom here, because I also do a lot of observing in the morning, and I like to know which of these charts works at what time in the morning. So this fall chart actually works really nice in late June, early July, around 5 o'clock daylight savings time, where July 1st is sort of the prime time for this exact position. I also mark what the right ascension time is for this particular chart. Again, for calculation purposes, it's helpful to know that. So once you get through all of the 6 charts for the different times of year, for each season, it shows you the typical things we teach people, like how do I find this, that, or the other thing in the sky? You're just learning. So you always start with some prominent thing that anybody can find in the sky, and then you start drawing lines in the sky to find other things. So there's one for the fall, there's one for the summer, winter, and spring. So this is the fall sky, and as we all know, the Great Square is probably the most prominent thing in the fall sky, and then from there you can find other things, including, hey, where's that Andromeda galaxy? So again, one of those things you typically want to teach somebody when they're first getting started. And then you have your moon map with all your prominent Maria and your prominent craters marked, and even where the Apollo landing sites were. So again, you can't ask for more in a simple guide that I think this costs like $10. I mean, it's a pretty amazing little piece of material that Jonathan put together. It even gives you a list of deep sky objects to start with, when you want to move beyond just the constellations, what time of the year you have your meteor showers, typically what days they are, a few helpful resources on the web, including his website, where he actually has some planet location charts that you can print out for each year. I think right now he has I don't think he has the 2025 ones up yet, but the 2024 ones are up. And as I promised, there are a few more stocking stuffers that he's created, and again, all very inexpensive. So the first one, I would say this, if you don't want to give somebody that book that I just showed you, this would be the book for, say, the early grade school person, 1st to 5th grade, and it's written in a story form, so you could actually read it to your young person. And what it starts with is this young girl, Sophie. She goes outside. It's very bright. She can only see a few stars. And so she asks her grandfather to explain about the constellations because she can't really see them. So he takes her out to the countryside, and he starts showing her the constellations and teaching her how to find them. So it kind of takes that those couple of pages that I showed you for like the fall sky, the winter sky, the spring sky, and puts it into a story form to get children involved, because every child loves stories. So it's a way for them to start learning the night sky as a young person. Next up, I would say after that age group is this book here, Stargazing for Kids. This is much more detailed. This is, I think, about 120 or 130 page book that really gets into more detail. Like, there's a couple of pages on every planet, on different types of objects in the sky, talks about the constellations, talks about a lot of deep sky objects. So this is more a full field guide, as it says here, to astronomy. Following that is this fun little thing here. It's a deck of playing cards where the images on the playing cards are the constellations, and along with that is what time of the year is best to look at that constellation. So you can play all kinds of games with this. You could do, just play cards with it, but also you could start using them like as flashcards, like just show it to them and hide the name and the season, and say, okay, what constellation is that, and what time of the year do we see it? So that's can be a very fun tool for, again, getting kids engaged in astronomy, even for ourselves. I mean, sometimes I forget what a particular constellation looks like, and that could be a good memory tool for you. The last stocking stuffer, this is kind of his premiere book. This is for adults. This is about 300 pages long, I think, and it's a complete guide to every constellation. And he's organized it by season and also by ease of finding, right? So you start with the Big Dipper. You start with Scorpius. You start with Orion, and then progressively shows you more difficult constellations to identify, gives you tools and tips on how to find them, what time of the year to see them, how high in the sky they're going to be, what direction to look. It's pretty comprehensive. And with each constellation, he talks about other things in the constellation to look for: double stars, nebulae, galaxies. So again, and also very not expensive. So you complete range of stocking stuffers for the holidays, from first graders, all the way up to adults. One thing I will say is Jonathan is accessible. I've had numerous conversations with him, via email. We even tried to get him to do a talk for us, but he's sort of taken a detour in his profession. As I said, he started off doing a lot of astronomy teaching for many, many years, but he decided to go a different direction. He now is a certified wildlife tracking teacher. So he goes around the country teaching people how to track wildlife, and he has a whole bunch of now animal tracking books as well. So
that's awesome.
happy shopping, Jonathan Popelle, www.jonathanpopelle.com. Check them out, and hope that you have a happy holiday.
Thank you so much, John. Yeah, it seems like there's a pretty big Venn diagram overlap between wildlife enthusiasts and astronomers, so I don't think that's a coincidence. Cool. Well, folks, we're running a little bit late tonight, but if you can stay with me for another 10 minutes, we have a lot of visual treats for you. It's time for our astrophotography showcase. Let me get that shared here and push all the right buttons. Hang on while I share my screen. Share. Yes, that screen. All right. Hopefully you can hear me and see slides. If not, somebody please yell at me in the chat. But yeah, let's kick things off. Hey, John Pinto, you're still up. You got some sea star stuff for us tonight.
Yes. So the other night, when we finally had a clear night, I decided to try out the new mosaic mode that was recently released on the Sea Star. And I had actually first tried it on the Andromeda Galaxy, which everybody was trying, but I never really got enough time on it. And so it didn't complete the mosaic. So this one, I believe, ran for a total of real time about 5 hours. I started it about 10 o'clock at night, and it went below my garage at like 2 or 3 o'clock in the morning. But luckily enough time that I was able to get the full mosaic. And I believe this would be about 2 degrees high and about a degree and a half wide. And the total integration time, as you can see at the bottom, was 130 minutes of that 5 hours. So one of the things that we've kind of discovered, both not just me, but the C-Star community, is ZWO must have done something in the C-Star software when it does mosaic to reject satellite subs. So there's no, for 5 hours, something must have gone through this field of view, but they must have all gotten rejected. Amazing little tool. Looking forward to the next generation of this, which will be the S30, which will have a wider field of view. So hopefully you'll see some of those coming up for me next year.
Looking at this from the perspective of a PixInsight geek, mosaics being that easy is just unnatural. I mean, that's like the hardest thing to do, doing it the old-fashioned way. So that's a pretty big technological achievement.
One of the things that people are realizing is if you tried to do this your own, because it does save the subs for you if you want to do it on your own, it's very difficult to get those all aligned, to your point, in processing software to get it all lined up correctly. And so we have had people who are expert astrophotographers who have these guys, they have stopped taking the subs. And they said, this is good enough. I could start with this, and then I'll post-process what it has stacked.
Yeah, I can't see the seams, so that's kind of amazing. Very cool. Thank you. Up next, we got Jeffrey Merrick. So go ahead and take yourself off mute because you've got some pretty cool stuff to show us here. Jeffrey, I know you're here.
Here I am.
There you are. Hey.
All right. Yeah, I have the Mac Newt 190 astrograph, and I bought it like 4 years ago with a G26 camera. And I want to try my luck at astrophotography. Well, there's a lot of learning there. This particular image was taken last year in May. And I think I was aiming for M84 or M86 at the time. And, that is at the end of the Markarian chain. I end up getting Op 120 in there, which is the EYES galaxy, which is a pair of interacting galaxies. So this is a cluster of galaxies all about 50 to 60 million light years away. And I took 18 subs, not many, at 5 minutes each exposure-wise. And really, many times I'm just limited to the number of exposures I can take. And because I usually don't like staying up after midnight mostly. So that's all I gotta say about this. This is one of several, then I start to focus on all the op galaxies, and there are quite a few out there, interacting galaxies. So
yeah, awesome results. I think you have the same scope I do, by the way. So
good same choice. Scope? Oh, cool.
You said it was a Mac Newt 190, right?
It's a 190 Mac Newt.
Yep, same one.
Same telescope. It's pretty good. I'm able to capture lots of things, especially in my light polluted backyard, where I can't have long exposures. I'm limited because the light pollution is just so bad. And it's a miracle that I'm able to capture these objects. So in this particular image, I was aiming for the twin quasars. Specifically, I had the coordinates, and I figured, well, let's aim for the twin quasars, see if I can pick them up. They're about magnitude 17. Again, light polluted skies in my backyard. And the twin quasars, for anyone who don't know, can be found in the constellation Leo. Oh no, that's the other one. Wait a second. Hold on a minute. Not Leo. Hold on a minute. There. It's located in the constellation Ursa Major. It was actually discovered in 1979 and first identified as gravitational lensing back then. Its distance is 8.8 billion light years away, and it's separated by 6 arc seconds. So as you can see, I'm pressing the limit of this astrograph, and it really works out pretty cool. And you also see the Frisbee Galaxy, I think they call that big thing, Frisbee Galaxy there in the foreground. And there are also a couple of other galaxies in the neighborhood. But the most fantastic thing was the twin quasars. This was taken. This particular one was 96 subs at 2 minutes. So I learned that using 2-minute subs instead of 5-minute subs works out a lot better.
Absolutely. Yeah. Tracking is a little bit more forgiving then too.
Yeah, it is. It is more forgiving then too. So yeah.
But yeah, 8.8 billion light years away, people. Think about that for a
actually,
minute.
there's 2 other quasars in the neighborhood that's made it to 7.5, and I did capture them, but I just wanted to show just this one. There's 2 others out there just that I captured in this image too.
Wow. Very cool choice of a target. Thank you so much, Geoff. Up next, John Starr. Whoa, look at that. What do we got here?
Hey, good evening. So this is sort of a streak shot. I took this. This is Starlink Group 810, and I took this 3:43 in the morning from the Marina Park in Titusville. And this was kind of a fun shot. I thought for sure all those clouds were going to blow in right before because I could see them coming, and I thought for sure it was gonna cloud out, but they held off long enough for me to get this shot. This one was kind of fun because if you look at it, there's some neat things in here. You can see Jupiter sort of at the top of the streak there, and Mars is sort of right below that on the, I'd say it's sort of in the center, the top of the streak there. And you can see the constellation Orion, and you can even see a little bit of nebulosity there, and that's just to the right of the streak. And so this is a composite shot. The streak itself, I took this with the Canon EOS RA with a Canon 16 to 35 millimeter at 16 millimeter f/18, 240 seconds ISO 100. And then I took essentially 7 shots of sort of the foreground and sort of the star field and stacked those. And so and then added that back. Otherwise the stars would have been streaked. And I really kind of wanted to show sort of the Orion Nebula and Jupiter and that kind of thing. So it is a composite shot, but I did take it. I took everything within a minute of finishing the streak shot. So what's interesting is whenever I'm shooting these shots, there's almost always other photographers around, and I didn't see a soul the entire time I was there. I didn't see another person. So this was kind of a neat, tranquil shot to take.
Yeah, that sounds like a great experience, and wow, that's just beautiful framing too. Like, great job.
So I would say, yeah, I actually took 3 cameras, and I took three different shots with 3 different cameras. 2 with 14 millimeters and this one with a 16 millimeter, and so I had some to choose from. So they were all slightly different in terms of the framing.
Very cool. And we got some deep sky stuff.
Yeah, so this one, NGC 6914, really pretty reflection nebula in Cygnus. This one I took with the 92 stowaway. It's about 18 hours of total immigration, 5 hours each in RGB, 3 hours in HA. I actually took way more than that, but I ended up throwing out a lot of subs. I don't normally shoot broadband. I took this with the ASI 6200 mono. I ended up throwing a lot of them away, and the gradients were really difficult. So that it took quite a while to process, but Really happy with how it came out. That adding sort of that hydrogen alpha really kind of made the nebulosity sort of pop there, the emission part. So really happy with this. It's a really beautiful area of the sky. Cygnus is one of my favorite places to sort of shoot.
Absolutely. And yeah, those reflection nebulas can be a tough one to capture. So nicely done. And we got yep, the Heart Nebula.
Yeah, so this one essentially IC 1805 and Heart Nebula in Cassiopeia. I took this with a camera lens with a Rokinon 135, stopped down to f4 with a one-shot color camera, an ASI 533 MC, which is a really fun little camera to use. It's very forgiving. I used the Optolong L-Extreme dual narrowband filter and on my Star Adventure GTI. It's such a wide field setup. It's very forgiving in terms of tracking errors. And so this is about 15 hours total exposure time, and process this in PixInsight and in Photoshop. And so I'm telling you, it's a lot of fun to use that Rokinon 135 because it's just so easy. It's so easy to carry around. It's so lightweight. The setup time is super easy. You can see a little bit of the Sol Nebula there. I thought long and hard about doing a mosaic, but it's just such a pain in the butt to
Yes, it
do
is.
the mosaic. We were talking about it earlier
Yep.
with John. So I decided not to and just focused on sort of the Heart Nebula.
Beautiful. And I ended on that one for you on purpose because this is a great example of one-shot color narrowband image processing, which you'll be talking about in a week, right?
That's right. Yeah. So we'll talk about all the tools and sort of how we did this.
Yep. So if you haven't signed up already, check out Groups.io, the calendar there, and 7 p.m. next Wednesday, right, on the 20th.
That's right.
So we'll be there. Thank you so much. Wes, our newest board member at large. Check that out.
Hello, hello.
Hey.
Hey. So, yeah, this is NGC 7331 and the Stefan Quintet, that little galaxy group that was made famous most recently by James Webb, that really cool looking image they did, one of the first ones. I think I shared this image with the club in like January or February. I can't really remember. But I only had like 2 hours of L on it, so I was always disappointed. Like we just ran out of time because of the clouds, terrible year we've had. And well, the clouds cleared up a little bit this fall, and I added some more time. I think I added about 10 more hours of L, and it really helped bring out some of the detail and bring down the noise in those little guys there, and especially on the edges of the big galaxy there, NGC 7331. Made the detail a lot better, reduced the noise. It turned into a much better image, one I was finally happy with.
Yeah, as it should be. It's that's gorgeous. Lots of detail there too, and really rich colors as well. So nicely done. Speaking of rich colors,
And there we go. We have Sharpless 101, I think is the name, the Tulip Nebula. This is your pretty typical emission nebula. There's a star, maybe a couple there in the center that are irradiating everything and causing everything to glow and be all beautiful like this and make it look like a flower. And I've always been intrigued by this one. I always wanted to get it, and it was a little dimmer than I expected it to be. I was a little surprised at how much I had to stretch and massage it to really get it to come out nicely, but I think it turned out pretty well. And just off to the right, if you imagine like off in the blackness off the edge there, is that Cygnus X1 quasar, I think it is, that has that like blue bow shock. I thought I
Yeah.
included it in the frame, but I missed.
We'll just have to do a
I really
mosaic
like
now.
this one. I like.
Yep.
Yeah, I should do a mosaic. Yeah, I hear you guys. I don't want to do that too much.
Beautiful, beautiful. Yeah, I mean, this is a really challenging target, actually. Like, I think I had to throw about 25 hours at it as well. And making it actually look like a flower is also a challenge, too. So nicely done.
Yeah, I think this was about 25 hours, just short of. Yeah.
Yeah. Gorgeous, gorgeous, gorgeous. Hey, John Frank, are you here?
Yes, I'm here.
Cool. You've got a story behind these images.
I do. I will try to keep this short, but those members that know me and the board know I can talk a fly off a wall. So at least my kids tell me that. So I am making this a simpler time. I'm trying to learn to do these deep space photographies before Christopher Hunt. who's mentoring me, is learning that I am not the best student to be. Being the youngest of six, the word patience is not in my vocabulary. Anyway, so what I did was I just wanted to show a couple quick photos of what you can do with your iPhone. And this one actually, I was driving back from Atlanta. I used to live there, and I stopped at the rest area, the first rest area in Florida. And I know it's up near a national park. I can't remember when, but I was just going to be there for 10 minutes. I got out of my car, and lo and behold, I was under a light that was out, and you could see the Milky Way galaxy. And it has been years, not years, but it's been a long time since I've seen it. So I started freaking out, and the brightest part of it was up. So I just zoomed in with my iPhone. I have an iPhone 12, whatever it is, Pro with the three lenses. And this was one of the pictures I got, zooming into the gold area of that. So I was pretty taken back. And needless to say, it was supposed to be a 10-minute stay at this rest area. As I continued to stay there, security came out and started questioning me on what I was doing. And I actually got them to look at the photos. So they were looking at them with me. But an hour and a half later, I left the rest area and got back at 1:30 in the morning. But it is crazy what you can do. So
Yeah,
that's
that's
this
amazing.
one. Yeah.
Yeah.
This is an advertisement for Christopher Hunt's Loner Scope contest. I took this. I don't know if y'all remember the emails you had flying around about the large sunspot group that was out there. So I set my telescope out in the driveway pretty quick and actually did the exact same iPhone smash to the eyepiece. And this is what the photo I got. So please submit your photos. We're having a first place is Telview eyepiece, and then second place is a $75 gift card, and then a third place a $50 gift card to Gina Astro. So those of you who are new and all that, or even if you aren't, try it. It's a lot of fun. Takes a little patience, but
Wow, those are good prizes. I didn't even know about that. Very cool.
yeah. This was walking out. This didn't turn out on here as well, but this was just walking out my front door the one night, and there was a double halo around the moon. So I grabbed my iPhone again, and I was out there for about half an hour taking pictures of this. Um, So again, you never know what you can get with the iPhones this day and age. I mean, it's a lot of fun to just have those with you. I'm
Yeah,
probably
that's
going to go
great.
into photography too, another rabbit hole that'll eat all my money, but I like just taking regular pictures.
It's definitely good at doing that.
And then this is the last one. Again, this was another night that's coming out my front door of my house. I just happened to see the clouds and everything around, so I just grabbed my phone and started taking some pictures. I have quite a few, like through the palm trees, and I have the moon and all that. But it's amazing what the iPhones can do. So if you're on your way wanting to do photography and everything, it's a great start to just fool around and see what you can get out of your iPhone, and then advance to the other stuff. And that's
Yep.
it.
Thank you so much, John. Yeah, it's a great way to get started and some pretty pictures too. Speaking of pretty pictures, Richard Wright, what do we got?
This is the Wizard Nebula. So this is actually, it's about 9 hours worth of data I collected over September and October. Some here at my house and some down at my dark sky camp near Cassini Prairie Preserve. It's actually less than half an hour of RGB. I used a monochrome camera with chroma filters, the Player One Poseidon M. And I got a bunch of HA and O3 that I mixed with it. And I did kind of like the synthetic RGB, I guess. You know, you map the hydrogen to the red. A little bit of the hydrogen can actually go to blue for hydrogen beta. And then the O3 you map to green and blue both because it's cyan. So it gives you a natural color palette. Obviously, you know, you saturate it a little bit and you tweak it around and all that sort of thing. But I don't know how many years I've been trying to get a good Wizard Nebula, and I always end up with a whole bunch of HA and never get anything else to mix with it. So this year I just made it a priority. Telescope was an Esprit 150 from Skywatcher. and I have a 0.77 reducer. Skywatcher makes a reducer specifically for it, so it brings it down to f5.4. And yeah, a bunch of O3, bunch of HA. The HA exposures were actually the longest. They're only 3 minutes. And the O3 exposures are 60 seconds. And the RGB color was also 60 seconds. And I kind of cheated a little bit. Same scope and camera, but some of it I took on a Paramount Mighty, and some of it I took on a Skywatcher Wave 150 strain wave mount, which really it's at the end of its capabilities with a 6-inch refractor on it. But I was happy with it, so I'd send it in. Here you go.
Gorgeous. Yeah. One of these days I'm going to
Thanks.
interrogate you on how you get those stars to be so tight and colorful with such small exposures. So that's really awesome.
Well, you need the short exposures to get smaller and colorful stars. If you expose too long, the colors saturate and they bloat out. The airy disk, the airy disk is also recorded by your sensor, but it's really dark. And if you expose it for a really long time, well, the airy disk builds up too. And then that's why stars get larger with longer exposures. It's the airy disk is actually polluting the surrounding pixels, not the actual star. So I always recommend very short exposures for the star field. And a tool that I was late to the game on the AI, but I finally got Star Exterminator. And I take the stars out and process the stars in the nebula separately. And then I drop the stars back on top of it. And yeah, when you take the stars out, it cheats because it fills in, where the stars were, but then you cover it up with the stars. So I feel like I'm faithful to the data, when I do that.
Yeah, I agree.
Yep.
How short were those subs for the RGB?
The RGB were 60 seconds. Sorry, 60 seconds.
Good.
Yeah.
And yeah, I don't think I've ever seen that like blue ball below the wizard's little nose there before. So that's a pretty cool result.
Yeah, I went looking on Astrobin, and yeah, a lot of people get that there. It came out kind of green, and I don't like to beat the images into being the color I want them to be. And it's just like, this is what it's going to be. There's also a little really bright loopy thing on one of his hands. It's in the raw data, but I don't see it on many other images. I've sent this to a couple of my experienced astrophoto friends and said, could you compare this to your data? Because I don't know what this is. Yeah, anyway, there's a little feature there that I got.
Very cool. Thank you so much, Richard.
Thanks.
And that is the end of the show tonight. Thanks for sticking with us, folks. And I hope to see a bunch of you on our holiday party on December 14th, right? Yes, Saturday. So we'll see y'all there. And in the meantime, keep looking up and think clear sky thoughts. Thanks, everyone. See you next time.